Last year, you guys spent a lot of time dealing with quadratics, and you might wonder, why are we learning quadratics? Well, they're sort of aimed at calculus, and calculus relies heavily on polynomials. So polynomials are functions. They could be quadratics. They could be longer than that. So I could have a 6x to the fifth, on and on and on. And it turns out that performing calculus on polynomials is extremely simple. Extremely simple. In fact, I could teach calculus on polynomials to a fourth grader, maybe fifth grader. Okay, so um, calculus itself is not a difficult idea, but sometimes the algebra and the trig gets really complicated. It's not necessarily the calculus that's hard, but it's performing the algebra and the trig. And sometimes performing calculus on a really complicated equation is either extremely difficult or simply impossible. Like, we don't have a method to do it. So instead, if we have a super complicated graph, we convert it into a polynomial. So let's say that I'm modeling some real world situation that looks like this, right? And I need to put that equation into a computer. I don't know, maybe I'm flying a rocket to the moon and that tells the fuel pump how much fuel to send to the rocket engine. I'm not sure. Well, that's a really complicated equation. So what if I were to just estimate it using an x to the third graph? Is that equation, you might want to pay attention to this, is that equation pretty much the same as the true equation? No. It's close in a lot of places, but it's certainly not perfect. So that could be an x to the third graph. Well, if I created an x to the ninth graph, I could make an equation that's much closer. Is that perfect? No. But if I need one that's more accurate, then I could, so let's say that was an x to the ninth. Well, what if I did an x to the 45th? Then I could create an equation that is so close to the real equation that I either can't tell the difference or I don't care that they're not the same. So I didn't know this until I took Calc 2. But in the real world, when we build complicated equations, it's actually easier to have an extremely long polynomial than it is to use the real equation, because performing calculus on polynomials is extremely easy. I honestly could teach it to a fourth or fifth grader. It's that simple. But doing calculus on a complicated formula or a trig formula that has lots of different pieces to it is very hard. So the reason we study polynomials so much is we can turn any difficult situation into a polynomial, and that polynomial might be really long. It might have 1,000,000 terms, but performing calculus on that is super simple. So that's why we study polynomials. Last year, you pretty much dealt with quadratics. Now we're going to move into larger polynomials, and those polynomials have attributes that we're going to start learning about today. So have you ever heard of the degree of a polynomial? What is the degree? The highest power. So in this case, the degree is 8. Why do we care? You two are not paying attention again. Why do we care what the degree is? Well, the degree determines the basic shape. So an x squared graph looks like this. It could also look like that, right? An x to the third graph looks like this. What would an x to the fourth look like? It would be a w. An x to the fourth would be a w. What about x to the fifth? Like that, and so on. And so the degree is going to determine how many direction changes are in there. Now, it does get a little bit more complicated than that. An x to the fourth could actually look like this. In fact, it's not a parabola. It's a little bit steeper than a parabola, and it's more flat at the bottom. And then an x to the fifth could look like an x to the third, but it would kind of have flatter. So we can't just look at a graph and say that's an x to the seventh, but we can look at a graph and determine, does it have an odd degree or an even degree? So all of the even degrees are going to have endpoints that go in the same direction. So an x to the sixth could look like this. So every time you have an x to an even, the ends are going to be going either up and up or down and down. And then if you have an x to an odd, they're going to be going in different directions. Okay? What about the leading coefficient? That is the coefficient in front of the exponent that determines the degree. So this is the leading coefficient. Why do we care? What does the leading coefficient tell us? It tells us if it's an up or if it's a down. So negative 2x squared is a sad parabola because of the negative. What does this do? Just makes it taller. Okay, but the negative means it's upside down. So if I had negative 5x to the fifth, I know quite a bit about this. I know it could have up to 4 direction changes, like this one. So I change direction 1, 2, 3, 4 times. What do I know about the endpoints? They're going opposite because this is odd. Is the left side up or down? So the overall graph is negative, which means the left side has to be up and the right side has to be down. And what happens in between? I don't know. But it could do that. It could just do that. It could just do that. We're not sure what happens in the middle. That's what all the other stuff is for. So this is going to determine what happens in between the endpoints. Okay? So why do we care? The degree gives us the basic shape. The leading coefficient gives us the direction, whether it's an up or a down. Okay? That will become important later. Okay? So I can factor this quadratic into v minus 4 and v plus 5, and then this one factors into 5 times v plus 7. So the roots of this are 4, negative 5, and negative 7. If I were to graph that, what would it look like? Well, it has to hit 4, negative 5, and negative 7. So negative 7, negative 5, and 4. It's a degree 3, so the endpoints have to go in different directions. But on the left side, does it start from the bottom or does it start from the top? The bottom. Why? Because the leading coefficient, right, if I look at all of the leading coefficients, they're all positive, so it would look like this. Okay. What if I were to square this? What would that do? Well, now it would be a W, right? Is it a happy W or a sad W? Happy W. Okay. So a happy W, I approach negative 7. What's going to happen at negative 7? So it's a duplicate root. There are 2 of these. How do I draw 2 roots in the same place? It bounces. So it's going to come down and bounce off of that. Then I need to change direction. What's going to happen at negative 5? Pay attention, Adam. You keep doing your work. You're going to want to know this stuff. So as I approach -5, how many times does -5 happen? Once. So it just goes straight through. Okay. Then I change direction. What happens at 4? Straight through. What if I change this to v minus 4 to the third? Kind of. Not straight through, but it's going to do an x to the third saddle, like that. So a single root just goes straight through. A double root is going to bounce, and a triple root is going to do this saddle that looks like an x to the third graph. What would fourth look like? It would be a bounce, and instead of a parabolic bounce, it's not really a parabola, but it sort of looks like a parabola. So if this is a double, then a fourth is going to sink faster and then flatten out at the end. So let me show you. So I'll show you the difference here. So if I graph x squared and x to the fourth and x to the sixth and x to the eighth. See that? So the blue one is the x squared. The higher the exponent, the steeper it falls, but the flatter it is at the bottom. And then the same is true with the odds. So if I were to graph an odd, an x to the third might look like this. And then an x to the fifth would be steeper and flatter. Oh. And then an x to the seventh would be steeper and flatter, like that. All right. So here is a quadratic that has a whole bunch of roots. What are they? -7, +7, and this would be x minus 2 and x plus 2. So 2 and -2. Now later you're going to graph it. So we have a -7, a -2, a 2, and a 7. What is the degree of this polynomial? Not 2. How many x's are there? Well, how many are here? 2. How many are here? 1. And then there? So a total of 5. But wait a minute, I only have 4 roots. So which one is duplicated? -7 occurs twice. So I know my graph is a 5th degree. Is it a happy or is it a sad? Well, I guess it's not odd. Is it going up to the right or down to the right? Up to the right, because my leading coefficient is positive. So as I approach -7, what will happen? It's going to bounce. And then the rest, I just go straight through. Something like that. Ugh. When you graph a function that has multiple ups and downs, let's not do that. Let's do this. Okay. This point would be called the maximum. What is the minimum point of this graph? It doesn't have a minimum. It goes down forever. Okay? But it does have this point that is sort of the smallest point nearby. And then this is sort of the largest point nearby. So we call those local minimums and local maximums. Yes, this graph does have a maximum. But it also has a second point that is called a local maximum. It is the largest point around that area. Okay? And in calculus, those points are very, very, very important. So if we turn on, you can either use a handheld graphing calculator, or you can use the ALEKS graphing calculator. If I plug in the equation, so I need to move this. All right, so negative, I forgot where my variable is. Where, maybe I just push x. Negative x, and then raise that to the fourth, and I push right, plus 2x to the third, and then plus 3x squared minus 5x minus 1. Okay, I'm going to push graph. I have this graph, and now I want to find the maximum. So I'm going to click on Extrema, and it's going to ask me, where do you want me to look? So this point right here looks to be about negative 1. So I want to look between negative 1.5 and 0. So tell me the highest and the lowest point in that region. Oops. So negative 1.5 and 0. Find extrema. Okay, the maximum is negative 1.05, comma 4.03. And then the minimum is right here, which that doesn't really tell me anything. Okay, so if I want to find the next one, I want to look between 0 and 1. Let's do 1.5. It'll be easier to see. So the lowest point between 0 and 1.5 is 0.6 and negative 2.6. Okay. You can use the ALEKS calculator, but I highly recommend that you guys get a graphing calculator so you can use it on the ACT, because obviously you can't use the ALEKS calculator. So so if I go here, what was the equation? So negative, here's the X button on the TI graphing calculators. X to the fourth plus 2x to the third plus 3x squared minus 5x minus 1. And then I push graph, and I get that same curve. And then I'm going to push second calc. And this one, instead of extrema, it says, do you want a minimum or a maximum? So I want to do 4 maximum. And it wants me to pick a left bound and a right bound. So my left bound, I will pick 2, negative 2. And my right bound, I'll do negative 0.5. And you can see those arrows. And it says guess. So I think the closest answer is negative 1. So I will click negative 1, and then it will find that point, 1.05 and 4.26. Okay. All right. Okay. Here we have a graph that changes direction several times. Imagine you are riding a roller coaster, and the roller coaster travels in this direction. So here is my little roller coaster car. I'm traveling in that direction. We need to determine, when is the roller coaster going downhill, when is it going uphill, and when is it flat? Okay? And we're going to use intervals to do that. So how many sections of this graph are downhill? 2. So this section is downhill, and this section is downhill. Okay? And then this section is uphill, and this section is uphill. How many times is the roller coaster traveling horizontally? 3. Here, here, and here. And again, those points, those intervals are really important in calculus. Okay? So how do we describe that? Well, we use interval notation. So if I did 4, 6, what does that mean? If I said x equals 4, 6, that would mean on a number line, if I drew 4 and 6, I would not include 4, but I would include 6. Have we done this? Okay, those are called intervals. So open circles get parentheses and closed circles get brackets. So if you see y equals 2, 3, that does not mean the point 2, 3. That means all y values from 2 to 3. Open circles. Okay? So if we look at our roller coaster, when are we increasing? Which x values create a increasing moment for that roller coaster? So that would be every x from -1 to +1. So -1 to +1. Is the roller coaster going up the hill at -1? What's happening at -1? It's horizontal. So should we put a parenthesis or a bracket? Parenthesis, good. Okay, what about at 1? Is the roller coaster going up the hill? No, it's flat. Parenthesis. Are there any other sections where it's going up? How do we join two intervals together? We have a special symbol for that. It's called the union symbol, and it sort of looks like a U. Okay. When else is it going up the hill? From 3 to 5. Is the car going up the hill at 3? No, it's flat. Is the car going up the hill at 5? Let's look at it. Did it flatten out? No. It just sort of stopped. That would be a really uncomfortable roller coaster ride, right? Immediately stopping. But when the car gets to this point, is it facing up the hill? Yes. So that means this gets a bracket. Okay. What about decreasing? When is the roller coaster going down the hill? From x equals -4 to -1. Is it going downhill at -4? Yes. So that gets bracket. What about at -1? No. And then we'll union that with 1 to 3. Are we going downhill at 1? No. Are we going downhill at 3? No. And then when is it oh, I did the wrong question, but that's okay. Okay. Sorry, we'll get to that later. That's not what this is asking. I should have read the instructions. So it just wants to know, let's say this is a roller coaster that went into water and then back out. So when is the roller coaster above water? So it's above water here and here. When is it below water? Here and here. So is f of 3 negative? At 3 seconds, is the roller coaster under the water? Yes. For which values of x is the function at water level. -3, 0, and 2. For which values of x is the function underwater? So that would be this section and this section. So that would be -3 to 0, union with 2 to 5. Is the roller coaster underwater at -3? No, it's at water level. Is it underwater at 0? No. Is it underwater at 2? No. How about 5? Yes. And then later, we'll do an increasing and decreasing one. I jumped way ahead. I'm sorry, guys. Okay. All right, this is end behavior. So we basically want to know, is it an up, up, a down, down, or is it a down, up, or an up, down? So these are even, and this is a positive, and this is a negative. These are odd, and that's a positive, and that's a negative. So if I had -6x to the 7th, which one would that be? So this is odd, and this is negative. So it would rise to the left and fall to the right. Okay? So all you have to do here is look at the equation and then figure out which one is correct. This one's pretty easy. It's an x to the 4th, so it's either up, up, or down, down. It's a positive x to the 4th, so it would be rises to the left and rises to the right. Okay? You do have to be careful because sometimes they write these out of order. So if you look at number 2, it's in order. What is, or B, what is that going to be? A positive x to the 5th. What does that look like? Oh no, you were on your phone. Were they good looking? Oh, that's not worth it. So falls to the left and rises to the right. Okay. This one's a little bit tricky. How many x's are there? Not 2, 4. There's an x squared, and then there's a 3x minus 5 that is also squared for a total of 4 x's, and there's a negative out front. Falls to the right and falls to the left. It's a sad W. Those are called M's. Sad W's are M's, apparently. Okay, that's it. Get to work.